A velocity time graph shows the velocity of an object over a certain period of time. The gradient of a velocity time graph gives you the acceleration of the object, which is a measure of how quickly the velocity changes with time, and the area under a velocity time graph gives you the distance travelled. Here's an example. The graph below shows how the velocity on the y-axis changes as time passes. So this is obviously the graph below shows how the velocity in miles per hour of a car changes with time in hours. The first question asks us to calculate the acceleration of the car in the first 48 minutes of the journey. Now, if we look at the scale of the graph along the x-axis or the time axis, we can see that the graph goes up in 0.4s because in 5 squares there are 2 hours, so that's going to be 2 over 5, which is 0.4. So the graph is going up in 0.4s. Now, 48 minutes, if I convert that into hours, or better yet, if I just do 0.4 times 60, that will tell us how many minutes each square is worth, because there are 60 minutes in 1 hour. So we have 0.4 times 60, that's going to be 24. So every small square is worth 24 minutes. So in 2 small squares, we're going to have 48 minutes. So to work out the acceleration of the car in the first 48 minutes of the journey, we need to work out the gradient of the graph over the first 48 minutes. To do this, I can consider 2 points on the line between 0 minutes and 48 minutes. So I'll just do a little sketch of it here. We can consider the change in velocity, which is from 0, well, it's not from 0, it's going from 30 to 50. So that's a change of 20 miles per hour. And the change in time is just going to be being careful to have this in hours because I want my final answer in miles per hour squared. That's going to be 0.8 hours. So the gradient is going to be 20, that's our change in velocity or our change in y, divided by 0.8, our change in time or change in x, if you like. This is going to be the same as, I can multiply top and bottom by 10. This is the same as 200 over 8, which is just going to be 100 over 4, which is 25. So the acceleration is 25 miles per hour squared. In B, we want to calculate how far the car travels between 4 and 8 hours after starting off. So that's going to be from here up to here. So to do this, we need to work out the area under the graph because velocity times time or speed times time is distance. So if we work out the area under the velocity time graph, we get the distance traveled in that region. So we need to work out the area of this shape here. And there are 2 ways to do it. You could think of it as a trapezium, or perhaps more easily, you could consider it as 2 shapes. So we have shape A and shape B. Shape A is a rectangle, so to work out the area, I need to work out the width, which is going from 4 to 6, so that's going to be 2 hours, and the height, which is 70 miles per hour. So we have 2 times 70, that's 140. So it looks as though the car travels 140 miles in this time. And then in B, we have a triangle. The area of a triangle is half base times height. So the base this time is again 2 hours. And the height is 70. So I need to do half times 2 times 70, which is just 70. So the total area of the shape is 140 plus 70, which is just going to be 210. So the total distance travelled between 4 and 8 hours after starting off is 210 miles. Here's a question for you to try. Please pause the video now, and when you're ready for the answers, press play. Here are the answers. Firstly, we want the acceleration in the first 2 seconds of the race. So I need to work out the gradient of the graph in the first 2 seconds. The change in the velocity, or the change in the vertical direction, change in y, is 5 meters per second, and the change in the x direction, or the change in time, is 2 seconds. So the gradient is just going to be 5 divided by 2, which is 2.5 meters per second squared. That's the units of acceleration. Her deceleration in the last 3 seconds of the race, well, that's from 8 seconds to 11 seconds. So we need to consider the gradient here. Now it's sloping downwards, so technically this is a negative gradient. And we look at the change in y, or the change in velocity, which is 5, and the change in x, or the change in time, is 3. So the deceleration, at least in terms of an absolute value, is 5 divided by 3, which is going to be, right, 3 into 5 goes 1, with the remainder 2. So it's 1 2/3, which is 1.67 meters per second squared to 2 decimal places. And obviously, because it's sloping downwards, technically this is a negative gradient. To find the distance that she ran, we need to consider the area under the graph. And because we want the total distance over the whole race, we just need to work out the area under the graph. The easiest way this time is to consider the graph as a trapezium, because that's what it is. It's got 2 parallel sides, and there's a perpendicular distance between these 2 sides. In the formula booklet, you'll be told that the area of a trapezium is half bracket a plus b times h, where a and b are the 2 parallel sides. They can be either one, and h is the perpendicular distance which separates them. So here, if I just label the trapezium, we have A, so this is the top parallel side, going from 2 to 8, so that's going to be 6. B is going to be 0 to 11, so that's just going to be 11, and H is 0 to 5, which is 5. So to work out the area of this trapezium, which will give us the total distance travelled, I need to do half times 6 plus 11 times 5. This is going to be 1/2 times 17 times 5, which I can work out on my calculator as 0.5 times 17 times 5. This gives me an answer of 42.5 meters.